continue with benzene. So we saw yesterday when we were doing nitration that when you do dinitration, the nitro group goes on position number 3. If you remember, I showed you, goes on 1 and 3. Now, which position will the incoming electrophile or the functional group, whichever you're adding, side chain, whatever you're adding, where that would go, on which carbon would it go? That depends on certain things. So let's see, we have what we call electron donating and electron withdrawing groups. So we have electron donating and electron withdrawing groups. Now, what do we mean by electron donating and withdrawing groups? So let's take a benzene right here. If you have, let's say, a side chain X, right? So let's call this carbon number 1, carbon 2, 3, 4, 5, 6. Or you could also number it this way: 1, 2, 3, 4, 5, 6. Doesn't matter. However you want to number it. But where the side chain is attached, obviously that would be carbon number 1. Yeah. Now, if the X, which is attached already on the benzene ring, if this is electron donating in nature, so if X is an electron donating group, it will direct the incoming group. It will direct the incoming group on position 2 and or 4. So the incoming group will be directed to position 2 and or 4. Now, how will you know whether something is electron donating in nature or not? So if this X is electron donating, to this you are trying to add something, obviously that will undergo electrophilic substitution. Then whatever you're trying to add or substitute for hydrogen, that will go on position 2 and or 4. That's where it goes. Now, how do you know if this X is electron donating in nature or not? So saturated side chains. Saturated side chains means that where the bonds are single. So saturated side chains, for example, CH3, like saturated, all carbon bonds are single, or OH, because these are also single bonds, NH2. If you have saturated side chains are electron donating in nature. Yes. Now let's see if you have an electron withdrawing group. So for example, we have a benzene ring here. A benzene ring here. And let's say now this benzene ring, the X that we have, let's say that is electron withdrawing. So if X is an electron withdrawing group, so if X is an electron withdrawing group, it will direct the incoming group on position number 3. So it will direct the incoming group on position number 3. So let's say we have carbon 1, 2, 3, 4, 5, 6. Yeah, if this X is electron donating, it will send the incoming group on 2 and 4. But if this X is electron withdrawing, it will send the incoming group on position number 3. Now, how will you know which ones are electron withdrawing? So if you have unsaturated side chains, unsaturated means you must have a double bond somewhere. So if you have unsaturated side chains, for example, CO2H, for example, nitro group, for example, CHO, that is an aldehyde. These all include double bonds. And these are unsaturated side chains. These are always electron withdrawing in nature. And if you remember, nitro group, like you can see, is electron withdrawing. So the incoming group will go on position number 3. And is why, if you remember, in dinitration, you already had one nitro group here. And nitro is what? Electron withdrawing. So the new group that will come, that is again a nitro, that will go on which position? Position number 3. Had this been an electron donating group, then your incoming group would have gone on position 2 and or 4. Yes. But if it is electron withdrawing, it sends the incoming group on the 3rd position. And if it's electron donating, then it will send the incoming group on position 2 or 4. Clear? Now let's see, we've done benzene. Now let's see reactions of methyl benzene. What is methyl benzene? So it is basically where you have a methyl linkage or a side chain on benzene. So let's see methyl benzene. So this right here is a methyl benzene. So you have a benzene ring with a CH3. It's a methyl group. Now this is also called toluene. So this is also known as toluene. And there will be 2 sets of reactions that take place. So there would be 2 sets of reactions that take place in methyl benzene or toluene. The first set of reaction would be the benzene ring reactions. Yes. And the second set of reaction would be the side chain reactions. So there would be reactions of this benzene ring, and there would be another set of reactions which will be of the side chain. Now let's see toluene, and let's see the set of reactions. So we have a benzene ring and we have a side chain. So let's see the ring reactions first. So this is what we have. Let's see the ring reactions. So the reactions of the ring would be similar to the reactions we've already done in benzene. Yes. And what were the reactions of benzene? Combustion. It undergoes free radical addition and it undergoes electrophilic substitution. Now, similar reactions will occur in this ring as well because it's a benzene ring. But obviously not all of them will occur because this has the methyl side chain to it. So let's see the ring reactions of methyl benzene. So which ring reactions will this undergo? So the ring reactions include electrophilic substitution. So the ring reactions undergo what? Electrophilic substitution. Yes. So these are your ring reactions. Now in electrophilic substitution, we did 5 types. We did halogenation, we did nitration, sulfonation, Friedel-Crafts alkylation, Friedel-Crafts acylation in benzene. Let's see which ones will methyl benzene undergo. So the ring reactions include halogenation. So this undergoes halogenation. Yeah. In halogenation, you have chlorination and you have bromination. So you have chlorination and there is bromination. Then there will be what? Nitration. In benzene, we saw mononitration and dinitration. In methyl benzene, you will have mononitration and you will have trinitration. Right? And then, like benzene, this will also undergo Friedel-Crafts reaction. So let's see the Friedel-Crafts reaction. You saw alkylation and acylation. Those also occur in methyl benzene. So there would be alkylation and there would be acylation. So we have, what we don't have here is sulfonation. What we have extra, something different from benzene, is trinitration. That had mono and di. This has mono and trinitration. These are the ring reactions. Clear? So these are the benzene ring reactions. Now you also have side chain reactions. So let's see the side chain reactions. So the side chain is an alkyl side chain or a CH3. Yeah. Let's see the side chain reactions. So the side chain reactions include you will have oxidation and free radical substitution. So there will be two side chain reactions. You will have free radical substitution, just like you saw in alkanes and AS. You'll have it here as well. And there will be oxidation with KMNO4. So there would be oxidation with KMNO4 aqueous, and there would be free radical substitution. Clear? So you have methyl benzene, which undergoes ring reactions and side chain reactions. The side chain reactions include free radical substitution and oxidation. The ring reactions include electrophilic substitution, which types? Halogenation, mono and trinitration, Friedel-Crafts alkylation, and acylation. Now, let's see the side chain reactions of methyl benzene. So let's first see the side chain reactions of methyl benzene. So let's see. So you have two types, free radical substitution and oxidation. So let's first see the free radical substitution. Now the free radical substitution will require what? The reagent would be what? The reagent would be a halogen. Let's take chlorine. And what will be the condition? The condition would be UV light. So there is UV light and you require a halogen. So let's see the reaction now. You have methyl benzene. So you have methyl benzene reacting with chlorine in the presence of UV light. Now, when you have methyl benzene with chlorine, you'll be like, Miss, oh, can't the ring react with chlorine? Because we did chlorination in benzene as well. And you just told us that electrophilic substitution or halogenation occurs in the ring as well. But if you remember, chlorination of benzene that happened in the presence of a catalyst. Do you remember AlCl3 catalyst? Do you have a catalyst here? No, we are just using UV light. So this will react with the side chain only, all right, not with the ring. And what will happen? You know what happens in free radical substitution? One of the hydrogen is removed and replaced by a halogen. So you substitute it by a halogen. So this will become CH2Cl. And what will we be left with? One Cl from here, and we've removed the hydrogen from here. So you'll be left with HCl. Clear? Now, what do we call this? What is this product? This product is called chloro, because you have one Cl, and it was previously methyl benzene. So chloromethyl benzene. Or you can also call this benzyl methyl monochloride. So you can call this benzyl monochloride, or you can call this chloromethyl benzene. Clear? And this happens in the presence of what? UV light. Now, you can keep removing all the hydrogens that you have, right? So let's remove, we still have two more to go. So you can remove those. So you take this chloromethyl benzene. To this you add more Cl in the presence of UV light, and this will give you what? This would give you what? This would give you CHCl2 plus HCl. Yes? And this is called what? This is called dichloromethyl benzene. So you call this dichloromethyl benzene, or you can call this benzyl dichloride. Clear? Then you have one more hydrogen left. So you can remove that as well. So you have one more hydrogen left. Let's see. So you have CHCl2 plus Cl2 in the presence of UV light. And this will give you what? This would give you CCl3 plus HCl. And this would be called what? Trichloromethyl benzene. So this is called trichloromethyl benzene or benzyl trichloride. So you can call this either of these two names, trichloromethyl benzene or benzyl trichloride. You see, you removed all the hydrogens and replaced them with a halogen. Yes, this is what? Free radical substitution. Now, what will be your observation for these reactions? So let's see the observation for the reactions. You see, you're making HCl here. So you will get what? Steamy fumes of HCl. Now, it's not necessary that you use chlorine if you're using, let's say, Br2 in the presence of UV light. Instead of Cl, you'll get Br, and you will get HBr, which will also be steamy fumes. Yes? And if you're using chlorine, then you can say the green, yellow color of chlorine fades. Yes? So these are your two observations for free radical substitution. Clear? Basically, what's happening here is, if we see it in terms of radicals, let's see what happens. So you remember propagation. Initiation was forming the radicals in the presence of UV light. Then we had propagation. In propagation, what did we have? Removal of an H and substituting it with the Cl radical. So you had a CH3. This reacted with a chlorine radical. I'm showing propagation. You remove one hydrogen, so carbon takes its electron back and becomes a CH2 radical plus HCl. Yes. Now you have this carbon with a radical. This will now react with another chlorine molecule to make two radicals. One will be given off as it is, and the other will bond with this, giving you CH2Cl. Clear? So I'm showing one propagation step in terms of radicals. Yeah. So this right here is what propagation. And you remember termination was what? Where two radicals become a molecule. So this right here is what? Propagation. I'm not showing all propagation steps, just to give you an idea that this is propagation. You remember forming one product requires two steps in propagation. In the first one, you remove the H. In the second one, you replace it with a Cl. Yes? So this right here is the propagation step to form chloro methyl benzene or monochloromethyl benzene. Clear? Now, let's see the next side chain reaction. So we did the first one, which was free radical substitution. Now let's see the second reaction we have, that is oxidation. So the second is oxidation with KMNO4. So you use aqueous KMNO4 for oxidation. You haven't done this earlier. We didn't do this in alkanes or anything. Yeah. But you do remember that KMNO4 is an oxidizing agent. So you can represent it with a square bracket and an O. So this is how you represent your oxidizing agent. What will be the reagent required? The reagent required will be aqueous KMNO4. What will be the condition? The condition for oxidation reaction would be you heat under reflux. And what will be your product? Let's see. Your product would be benzoic acid. It would be plus water and plus or minus carbon dioxide. So you could have carbon dioxide or you could not have carbon dioxide, and we will see how we know that. Now, let's take the first example. The first example is you have methyl benzene. Now, this is also a side chain reaction. Yes? So you take methyl benzene, you react it with an oxidizing agent, that is KMNO4, and you heat under reflux. Yes? So you heat under reflux. This CH3 that you have on oxidation will become what? CO2H. Do you see this has become benzoic acid? From methyl benzene, we've made benzoic acid. All you got to do is make the CH3 into CO2H. That's it. Now, you will also get water. Now, how do we know whether we will get carbon dioxide or not? Let's see. Now, there's a ratio that you got to remember here. If you have one carbon on the side chain, that will require 3 moles of oxidizing agent to produce 1 mole of water. Do you see? You have one carbon on the side chain. So that'll require how many moles of oxidizing agent? 3. Giving you how many moles of water? 1. Now you'll be like, Miss, but what about carbon dioxide? There was one carbon here and you've made acid out of it. Do you have any extra carbons? No. You have no leftover carbons. Therefore, there is no carbon dioxide produced. Let's see another example. It will make sense when you should add a carbon dioxide. So let's take, now this is not methyl benzene. This is another alkyl side chain. So you have CH2, CH3. This is ethyl benzene. Now, how many carbons do you have here? You see you have 2 carbons. I told you one carbon in the side chain needs 3 moles of oxidizing agent. You have 2, so that will require 6 moles of the oxidizing agent. And you heat under reflux. Now you'll be like, oh, miss, will this make 2 carboxylic acids? No. Even whatever alkyl group it is, irrespective of the number of carbons, it will always make carboxylic acid here or benzoic acid. Even though there are 2 carbons here, it doesn't matter. It will still become benzoic acid. Now, 1 carbon gives you how many moles of water? 1. You have 2 carbons in the side chain here, so this will give you 2 moles of water. Now you got to see, are the carbons on the side chain balanced? Here you have 2, here you just have 1. We're not even concerned with the ring because this is a side chain reaction. So you see, your carbon is missing. You have 2 here and 1 carbon here. So you will add a carbon dioxide here, and now it is balanced. If you see, oxygens are also balanced. 6 over here, 2, 4, 6. Oxygens are balanced. 2 carbons here, 1 and 2 carbons on this side. Clear? Now, let's see another example. Let's see another example where we have 2 alkyl chains. So you have a CH3 here, let's say a CH3 here. I told you 1 carbon requires 3 moles of oxidizing agent to give you 1 water. So this would require how many again? 6 moles of oxidizing agent. 3 for this, 3 for this. Yeah. You heat under reflux, and what will you get? The CH3 will become CO2H. This will also become CO2H. Yeah. Each carbon gives you 1 mole of water. So 2 carbons will give you 2 moles of water. And there will be no carbon dioxide produced because the carbons are balanced. 2 here and 2 here. It's balanced. Clear? Let's see another example of oxidation. In fact, I want you guys to try this. If you have an ethyl linkage here and a methyl linkage here, what will be the equation on oxidation? Try it. So let's see what we will get. Now, how many carbons do we have here? 1, 2, 3. Yes. I told you that 1 carbon will require how many moles of oxidizing agent? 3. So you have 3 carbons here. Therefore, how many moles would be required? You would require 9 moles of oxidizing agent. And this would become what? This would become CO2H. I told you, irrespective of the alkyl linkage, it will become CO2H. This will also become CO2H. Each carbon gives you 1 mole of water. So you have 3 carbons, so you have 3 moles of water. Now if you see the carbon dioxide, you have 3 carbons on the side chain. You have 2 here. So 1 is missing, so that would become what? Carbon dioxide. Clear? Let's see this. You have 1, 2, 3, 4 carbons. Each carbon requires 3 moles of oxidizing agents. So 4 will require 12 moles. Then you make your product. So you have 12 moles of oxidizing agent. And what will be your product? Let's see. So you will have this, which will become CO2H. You have this, which becomes CO2H. And you have this, which becomes CO2H. Each carbon gives you 1 water. 4 carbons will give you 4 moles of water. Now you have 1, 2, 3, 4 carbons here, and you have 1, 2, 3 carbons here. So the 4th carbon would be what? A carbon dioxide. Therefore, these are your products on oxidation. Is this clear? Do you guys